Good day, future engineers. Welcome to another session for Chemistry for Engineers. Today, we will be tackling about the periodic table and the periodic trends. This is the modern periodic table. Based on the developments, the elements are arranged in increasing atomic number and increasing atomic mass. They are also arranged in similar patterns according to rows and columns. Right now, there are 118 known elements in the periodic table. The periodic table has 7 series arranged in increasing atomic number and atomic mass, while they are arranged in 11 groups as according to their similar properties. The groups include Group A, which is your alkali metals, Group 2A, which is your alkali earth metals, 3A, boron group, 4A, which is your carbon group, 5A, which is your pnictogens or nitrogen group, 6A, which is your chalcogens or oxygen group, 7A, which is your halogens, 8A, which is your noble gases, and B group, which is your transition metals, LA series, which is your lanthanide series, and AC series, which is your actinide series. The next concept we have to learn about is the periodic trends. They are specific patterns or trend in the properties of the chemical elements. One of these patterns is the arrangement of the elements in a column that have similar electron configurations, or in other words, they have the same amount of electrons in outermost shell. Looking at the pattern on similar configuration, we have what we so-called the S, P, D, and F blocks. Hence, by just looking at the position of the element in the periodic table, we can easily determine their configuration. Another way of looking at the periodic table is through their metallic properties. This is a way to classify elements in the periodic table, which is the reason why there are metals, nonmetals, and metalloids. Properties of this classification are discussed in the learning module previously given. The pattern for this property is increasing down a group and decreasing across a period. Hence, looking at the periodic table, the blue ones are the elements classified as metals, the green ones are the nonmetals, while the elements intermediate of the colors blue and green are the metalloids, otherwise known as the semimetals. Remember that metals in their ion structure usually forms positively charged particles known as cations, while the nonmetals form the negatively charged particles known as anions. Metals usually give up their electrons, while nonmetals are most likely to accept electrons. This time, we will be discussing the major patterns in the periodic table. These periodic trends are the properties of elements in the periodic table that follow either increasing or decreasing pattern across a period and down a group. The 4 concepts under this category, which includes the atomic radius, ionization energy, electron affinity, and electronegativity. We will look into them one by one as we proceed. The first one is the atomic radius. It is defined as the size of an atom. Sometimes it's also defined as the distance from the center of the atom, which is the nucleus, to the outermost electron. The trend for this is it is increasing down a group and decreasing across a period. Looking at this periodic table, based on the trend, the smallest atom is helium and the largest atom is francium. To understand this further, comparing carbon, nitrogen, and oxygen, which will be the largest among the 3? Arranging them, carbon will be the largest, followed by nitrogen, and oxygen atom is the smallest. On the other hand, if among the elements sodium, potassium, and rubidium, sodium will be the smallest, followed by the potassium, while rubidium is the largest. Atoms, in order to achieve stability, forms ions to make chemical bonding possible. The sizes of ions vary from the original atomic radius, which is known as the ionic radius. The trend is, when an atom turns in an ion, the size increases, while if the atom turns into cation, the size decreases. On this slide, you will see how the ionic radius vary with the ion form. Looking at the metal parent atoms, the original atomic radius is larger than their ionic radius. It is shown by the color representations from brown to red. This is for the reason that when metals give up their electrons, the electrons leave the shell, this shortening the distance between the nucleus and the outermost electrons. On the other hand, opposite happens for ions that accept electrons into their orbitals. Hence, the increase in the atomic radius as is illustrated by the change in color from brown to blue. The next part of the discussion focuses on the trend called ionization energy. This is the minimum amount of energy needed to remove the outermost electrons from the valence shell. The pattern for this trend is that it is decreasing down a group and increasing across a period. Another important thing to note about ionization energy is the fact that it is easier to remove electrons if they are far from the nucleus. The small effective nuclear charge in an atom allows the ease of removing an electron. Hence, looking at the graph, the atoms with a large atomic radius requires less energy to give up their electrons, which is best characterized among metals. On the other hand, the graph peaks are represented by the noble gases such as helium, neon, and argon. This is for the reason that the noble gases possess the ideal configuration based on the octet rule. For this reason, they require a very high amount of energy for their electrons to be removed. Looking then at periodic table and the given pattern, it can be easily deduced that helium has the highest ionization energy while francium has the smallest. In this sense, anions of the nonmetals have the least tendency to give up their electrons, hence their high ionization energies, while the metals have small ionization energies because they have higher tendencies to give out electrons. So comparing then carbon, nitrogen, and oxygen, oxygen has the highest ionization energy while carbon has the lowest. While if you are to compare sodium, potassium, and rubidium, rubidium has the lowest while sodium will have the highest. The next focus of our discussion is called electron affinity. It is known as the measure of the tendency of an atom to attract an electron. It is also describes the energy change that occurs when an electron is accepted by an atom. The pattern for this is decreasing down a group and increasing across a period. Now looking at the periodic table, electron affinity has the same pattern as ionization energy. So which element has the weakest electron affinity? If you're thinking of francium, well, it's correct. On the other hand, which then has the highest electron affinity? If you're thinking of helium, unfortunately, that's incorrect. To understand this, we have to remember that helium and the rest in its column are noble gases for a reason. Since they are already stable, they have no interest in receiving electron. As such, fluorine then has the highest electron affinity. Comparing carbon, nitrogen, and oxygen, oxygen has the highest affinity for electrons, while carbon has the least. On the other hand, looking at sodium, potassium, and rubidium, sodium has the highest affinity for electrons with rubidium has the least. In general, nonmetals have higher affinity for electrons as compared to metals. The last trend included is so-called electronegativity. It is the ability of an atom in a chemical bond to attract electrons towards itself. It is said that the farther the electron from the nucleus, the weaker the attraction. the lower the electronegativity. The pattern is given by decreasing down a group and increasing across a period. Electronegativity follows the same trend as ionization energy and electron affinity. But just like in electron affinity, electronegativity talks about the possibility of chemical bonding. Hence, this makes the noble gases exempted from the trend again, since they are already stable and they don't need to attract electrons to complete their orbitals. In this case, fluorine has the highest electronegativity while francium has the lowest. So, characterizing the elements in general, non-metals has higher electronegativities than of metals. Summarizing the trends, we then have these common patterns as illustrated on this slide. Atomic radius has an increasing pattern as we go down a group and from right to left of the periodic table giving. On the other hand, ionization energy, electron affinity, and electronegativity gives the pattern that is increasing across a period and from bottom to top of the periodic table. It is important to note that noble gases are exempted from the trends in terms of their ability to participate in chemical reactions, since they already have a stable configuration. That's it for today. I hope that you learned much from this discussion. See you again next time. Stay safe and God bless.